Okay, well, hi everybody. Let's jump right into Chapter 13. Chapter 13 is RLC circuits. So a lot of Chapter 13 will be pulling together the past two chapters, Chapter 11 and Chapter 12, which were RL and RC circuits, and we'll pull them all together to have RLC circuits. Um, Also, as soon as we get near the end of this chapter, I will show you the much awaited, anticipated method of analyzing these problems using complex numbers. And you will see that it's easier than remembering all the different phasor directions that you have to draw right now. But you have to learn a little bit of math, but it's not too bad math. Okay, so proceeding on ahead. Sorry I'm not here. I am in Japan this week, but meeting the Japanese students that are going to spend 3 weeks with you in February, which will be pretty cool. Okay, so series RLC circuit, as you can guess, that means there's a resistor, inductor, and a capacitor in series with each other. And it doesn't really matter what order you put the parts in, that's still a series RLC circuit. Sometimes it does matter the place that you put the direction that you put the capacitor in the circuit. As you know, sometimes capacitors are polarized. So basically the way you analyze this circuit is that, let me get my pen here. So you have to find, once again, a total reactance or a total X. Only this time it's going to be the difference between the inductive reactance and the capacitive reactance. So there's inductive reactance and there's capacitive reactance. And so it doesn't matter whether you say XC minus XL or XL minus XC, but the reactance total, is going to be absolute value of the difference between the two. So if you subtract XL from XC, or let's say if you subtract XC from XL, so and this value is 100 ohms and this value is 200 ohms, you would get a negative number. So you just have to take the absolute value of that and make it a positive number, and that will be your total reactance. So then, similar to the previous two chapters, we have a total impedance. This is impedance. The total impedance, Z, in ohms, is still the square root of R squared plus X squared. But the reactance, X, is defined by the difference between the capacitive reactance and the inductive reactance. And we'll still have a similar formula, same formula for phase angle, only it's X total divided by R as the argument of the inverse tangent function. And the same definitions still apply, that XC is 1 over 2 pi FC. F is in frequency in hertz. C is capacitance in farads. And then XL is still 2 pi F. F is frequency in hertz. And L is inductance in henries. So example, let's do our first example. Determine the total impedance of this circuit, and then tell me, is the circuit more capacitive or inductive? And this is going to become quite important to us. Draw the phasors and observe what the voltage and which voltage and current components lead and lag. So also remember our previous formula, Eli the Iceman, that we used. Eli the Iceman, this little mnemonic helps us to remember who is leading and who is lagging in a particular circuit. So in an inductive circuit, voltage, by an E, voltage leads current in an inductive circuit. And in a capacitive circuit, current leads voltage in a capacitive circuit. But now we have an RLC circuit, so we have to find out what the total reactance is and then decide if it's more capacitive or inductive, and then we will apply the appropriate relationships to the circuit, and we will know whether the current or the voltage leads overall in the total circuit. So let's go ahead and do this problem. First thing is to determine the total impedance, and so we always start by having to find the reactances. So reactances in ohms. XL equals 2 pi F times L. And here's our L, 0.1 Henry. We have our F is 1 kHz, so XL is 2 pi 1000 times L, and L is 0.1 Henries, and we just do the math, and we get the answer, 628 ohms. And we find XC. XC is 1 over 2 pi FC in ohms, reactance in ohms, 1 over 2 times pi times 1000 hertz times 0.56 times 10 to the minus 6, because it's microfarads, and we calculate that, and we 284 ohms. So now we find X total. Reactance total is the absolute value, which you can also make, it's the symbol of two straight bars. Absolute value of XC minus XL. Doesn't matter which way I do it, so I'm going to say XL minus XC. But it's absolute value, so it's the absolute value of 628 ohms minus 284 ohms. And we get the X total as being 344. Now, is it inductive or capacitive? The way you tell is the inductance is more than the capacitance. So inductance right here is more than the capacitance. So it is an inductive circuit at this frequency. So it's inductive. Note that if I'm at a different frequency, the circuit may behave more capacitively, but at 1000 hertz it's behaving inductively. And continue, we have to find total impedance. So Z total is square root of R squared plus X total squared. So we have R, we have X total, we do the math, and we get square root of 560 squared plus 344 squared gives us 657 ohms. And we, thinking of this as a triangle, our impedance phasor diagram, we have an arrow that's 560 ohms long along this horizontal axis. This is the R. And then we have an XL that's 600, well, let's go back. XL is 628 up this way. That's XL, right? But if you look at it, then XC is 284 this way. This one, these two have the effect of subtracting one another because they're in opposite directions. So it's like doing math on a numbers line. You go 628 that way, but you have to go 284 down, so they subtract, and in the end you get, let me change my color so you can see it better. In the end you get a resultant amount right here, XL total, of 344 ohms in the inductive direction. And if we were to complete this phasor diagram for impedance, which is what we're doing, it would be completing this triangle out here, and that would be Z total. So Z total, the impedance is 657 ohms, and it is more of an inductive circuit than a capacitive circuit. So we still have to find phase angle. It's not enough just to say I found Z total, because total impedance would have to be both a magnitude, a number, and the angle that's associated with it. That's how you would completely specify total impedance. So the angle is tangent to the -1 of X total over R. And if I look at the triangle, I should draw that bigger so you can see it. If I look at my impedance triangle, tangent is opposite over adjacent. So opposite is in the XC direction, adjacent is the R direction. The angle that we're interested in is right here. And so I plug the numbers in and I'll get the angle is 31.6 degrees. 31.6 degrees. And it's inductive. So if it's inductive, what is the current and voltage components? What are the current and voltage components doing? We look at our little formula. Voltage leads current in an inductive circuit. So current is still in the direction of R. I'm going to redraw my picture here. R is in this direction. X total is in this upward direction. I is along here because we're in a series circuit and there can be only one I, right? And voltage leads. That means voltage must be along this direction. Voltage is along that direction and it's leading current. Let's see how my picture came out. Oh, I didn't get the picture. I thought the book asked for that relationship, but it didn't draw the picture. Okay. All right, so looks pretty familiar. The only difference between the past two chapters is fine. Actually, let me make that clear. Here's the problem redrawn again. I'm going to make, can't seem to draw where I'm sitting today. I can't draw. Try again. Let me make that clear because last page wasn't very clear. So if we're going to draw the phasor diagram for that, we have R in the horizontal direction, and R was, I already forgot the values. R ended up being, well, R is 560 ohms, so you would draw an arrow that's proportional to 560. And then we had XC was down 284. And XL is up. XL was 628. That means we get a resultant. Let's switch colors here. The resulting XC minus XL was 344 inductive. So that means it goes up 344 ohms. That's X total. And that's XL, that's XC, and that's R. And so then you would go and you would draw as normal. Let's make R go to there. Our phasor diagram, you would get Z in this direction, and Z we calculated to be 657 ohms. And then a part that I wasn't clear about a moment ago on the previous slide is that I, of course, is in the same direction as R. Let's put R down here so it's very clear. R is in the same direction as I because current and will be in phase, and so VR is also in this direction. And over here we get V, but we get VCL is in this direction. So VCL is in that direction. So the combined voltage across the inductor and the capacitor. So VL from just the inductor would be up, and VC from just the capacitor is down, but we have a VCL across the combination capacitor inductor. And if we were to do the equivalent voltage diagram, voltage phasor diagram, we would actually have VR in this direction, VCL inductive in that direction, and VC source is in the same direction as Z. So V source is in the same direction as Z. And then we would actually have our phasor diagram correctly. So those are actually the three voltages involved in this circuit. Voltage across the resistor, voltage across this combination right here, VCL, made up of voltage here plus voltage here. And we'll have a little bit more about that in a moment. Bigger and bigger, capacitive reactance gets smaller and smaller. And so low frequencies, you can expect the circuit to behave more capacitively, and higher frequencies you can expect any circuit, any given series RLC circuit will behave more inductively at high frequencies and more capacitively at low frequencies. But there's a point right here where these two lines cross, where XC equals XL. And that's called the resonant frequency of the circuit. And it has some very special properties. So for one thing, X total equals absolute value of XC minus XL. So, but XC and XL are the same at resonance. So that means that X total must be 0. And what would the impedance be then of a series RLC circuit? Well, reactance is 0, so at that point the impedance of the circuit is purely the resistance of the circuit. So the XL and the XC cancel out, and we have a purely resistive circuit at the series resonant point. Let me see what my next slide is, because I'm going to make a point at that. Okay, going back for a moment. We will talk a little bit more about this resonance phenomena here in the next few slides. So let me just show you that. Find Z total at 1 kHz, 3.5 kHz, and 5 kHz. Note the change, how Z changes, the value of Z changes, and the phase angle. So for each one of those frequencies, you have to find XC, which is 1 over 2 pi FC. And at each frequency here, you have to find XL, which is 2 pi FL. So let's just do it. At F equals 1000 Hertz, 1 kHz, right? We will find that XC equals, if I just calculate it out, 7.23 K ohms. And XL equals 628 ohms. So right now, this is our lowest frequency. Is the circuit more inductive or capacitive? It's more capacitive because the capacitive reactance is larger. So it is behaving capacitively. Actually, it's behaving at that particular frequency equivalently like a RC circuit only. It's almost like the inductance isn't even there, but it is there. And if we find then XC total, which is the difference between XC and XL, or XL and XC, and we will find out it's 6.6 K ohms just by plugging in the numbers. And then Z, the square root of R squared plus X total squared, will end up being 7.38 K ohms. And we do the same thing. Oh, and phase angle. Phase angle, tangent to the -1 of X total over R, and we will end up with a phase angle of 63.4 degrees. And the circuit is capacitive, so if I were to draw impedance diagram, I would have an R here, and I have a small XL pointing up, a big XL pointing down from these two values, but the net resultant is an X total pointing down, making the capacitive circuit behave capacitively. I could do all the same calculations at F equals 3.5 kHz, and when I do that, I will find that XC is now 2.07 K ohms, so it became less capacitive, didn't it? And XL is 2.2 K ohms. Oh, so these are getting close to each other, getting close to resonance. And then X total, same formula, will end up being 130 ohms. So notice we're close to resonance right now, and the reactance is almost canceling out right here. So at 1000 hertz, reactance was 6.6 k ohms, but at 3.5 k hertz, it's close to resonance, and the reactance is almost canceling each other out. And at that point, the angle will be 2.26 degrees. So it says that current and voltage are almost in phase with each other at this point because the angle between them is very small. But at this point the circuit is still more, at this point the circuit has become slightly more inductive. So it's slightly more inductive. That means current lags Vs by 2.2 degrees. And then finally at F equals 5 k hertz, I'll just put out the numbers real quick because I want to make the point. Xc will end up being 1.45 k ohms. Xl will end up being 3.14 k ohms. So I've become more inductive. As I said, higher frequencies, the circuit will become more inductive. X total, I'm off resonance now. X total is creeping back up, 1.69 k ohms. And Z total, 3.71 k ohms. I forgot to put Z total over here. This was 7, this was 3. This one had Z total being 3.3 k ohms. So Z is bigger at the slow frequency, Z is smaller at the close to the resonant frequency, and now Z is climbing back up again. And now the angle, if I compute the angle, is 27.1 degrees, but now still current lags voltage by 27 degrees. So kind of interesting to note what is happening. We will actually have more on this and even more analysis of this behavior, this going from a capacitive circuit to an inductive circuit and passing through the resonant frequency. We will be discussing that more here shortly. So one of the things that to note is that, and I've already brought attention to it, the voltage in the inductor and the voltage in the capacitor are 180 degrees out of phase with each other. So they always subtract. But if I were to take a voltmeter and measure the voltage across the L and the C together, that voltage by itself, is shown right here, is always going to be less than the individual voltages measured by across each one of the components. But that's because they are 180 degrees and they subtract from each other, sort of like the same way that the reactances subtract from each other. Here it is drawn like you would see it on the oscilloscope. So this top brightest blue line here is the voltage in the inductor, but the voltage in the capacitor, if you were to look at it at the same time on the oscilloscope, is 180 degrees out of phase with it. And so this voltage, let me highlight it. Voltage in the inductor right here and voltage in the capacitor right here being 180 degrees out of phase with each other, they will subtract and you will get the net voltage right here, which is across the capacitor and inductor combination. So that's what's happening. That's what you would see on an oscilloscope. Find voltage across each component. Draw the phasor diagram. This looks like a good problem. So we have our V source, remembering that if it's an AC and it says V source is 10 volts, that is always RMS voltage. That is not your peak voltage unless it specifically says that. So they don't tell us what frequency this problem is at, but instead they've already computed the XC. So at whatever frequency this circuit is running at, XC is 60k ohms and XL is 25k ohms. And I have a resistor here that's 75k ohms. So just looking at this, is this circuit more capacitive or inductive? It's more capacitive because the XC is a bigger value. So I can find X total. It's the absolute value of XC minus XL, or vice versa, either way. So I say it's 60k ohms minus 25k ohms, and that equals 35k ohms. Z total equals square root of R squared plus X total squared. So Z total will be square root of 75 squared plus 35 squared. Z total will be 82.8 k ohms. So now, find voltage across each component. We just apply Ohm's law. So apply Ohm's law, keeping in mind that we have to do Ohm's law with reactances. So sometimes that modifies Ohm's law slightly, but so I must be total current, I total must be the source, V source, divided by Z total, right? Just like we've done before. So it's 10 volts divided by 82.8 k ohms, and we get 0.121 milliamps, which is 121 microamps. Now we apply Ohm's law to each one of the components in the circuit. So voltage across the resistor is I times R, just like always. And it's the same I, it's a series circuit. There's only one I in the loop. So it's 121 microamps. And you guys can correct the units, 75 k ohms. Make sure they all match if you're doing it. But you will get 9.08 volts. VL is I times XL. Same I, 121 microamps times XL, 25 k ohms, and that will equal 3.03 volts. And voltage across the capacitor, I times XC, and it's 121 microamps times 60 k ohms, and it will equal 7.26 volts. So this is equals, not a minus sign. So what do you notice? So for one thing, if I add these three voltages up, it is greater than the 10 volts, right? And you say, oh no, that disobeys Kirchhoff's voltage law. Well, no, that's not true. It's because, remember, VL and VC are out of phase with each other. So if you really wanted to check and they're out of phase with each other, and they're not in the same. They're not also in phase with the voltage across the resistor. So let's just double check what's really happening. So VLC, that means, like if I were to take my voltmeter and measure the voltage across the two of these, would be 7.26 volts minus 3.03 volts, and I would get 4.23 volts. Well, 4.23 volts plus 9.08 volts still does not total up to be V source. So what do we really have to do? We have to say, we have to consider the phase angle that exists between all of these components to get the correct total voltage. So if I wanted to double check myself, it actually turns out that V source will equal the square root of VR squared plus VCL squared. And as long as I don't use these exact numbers, because these have been rounded off. If I originally preserved the long numbers, we can check it, and it will come out to be 10 volts. If I use 9.08 and 4.23, it actually comes out to be like 10.01 something volts. So some round off error occurs in there. So that's really because you have to consider the phases between the voltages. It's not a straight application of Kirchhoff's law, but it is really. It's just the phase information is hidden in there. So this is a capacitive circuit. We still need to find the phase angle, tangent to the -1 of X total over R. I draw my picture. R is this way. R is 75 k ohms long. X total is 35 k ohms, and I said it was capacitive. That means we draw it down this way. X total. I go ahead and draw this. There's my Z, and there's my angle right there, and which is X total tangent to the -1 of opposite right there over adjacent right there, opposite, adjacent, opposite, adjacent. Tangent to the -1 of that will give me the angle, and angle is right here. That's the angle. And I do that math and I'll get 25 degrees. And it's important to say it's 25 degrees capacitive, which means that current leads the voltage source by 25 degrees. Right, because why? Because, draw that a little bit more. The voltage source is in phase with Z, and current is in line with R right here. So current leads the voltage source by 25 degrees. This is the picture your textbook has for this problem. I think it's difficult to figure out what's going on from this problem personally myself. I would not have drawn it that way. If I would have drawn it, I would have drawn it by putting, in the end it's all the same thing, which you saw what I did. I had VR here, I have R here, I have I here, and then I have Z calculated this way, and this is at 25 degrees. So that's exactly the same as this VR, I. But what's weird is that R doesn't really go in this direction, but there's that 25 degrees. So there's the same 25 degrees. So it's like the author's phasor diagram is rotated 25 degrees from how I would normally draw the phasor diagram. I would have put VL here, I would put VC this way, and all of these same angles will still come out. Like this will still be 65 degrees, it'll still be between here to here, will still be 115 degrees. So it's the same as your author's picture on page, it's on page 587. So this is the picture your author has. This is the way I draw it because I always reference everything to the resistor, but if I reference everything to the source, which is also fair, then it rotates all of my phasors by that amount, by 25 degrees. But it is fair to do it this way. It depends on where you call your reference point. If I say, where is the voltage across the resistor compared to the voltage across the source, I could see the same 25 degree relationship. So both are fair. It's whatever works for how you think of the circuit, I think. Okay, so let's go back to talking about the resonant frequency that occurs. So what you do, I said it's the frequency where the capacitive reactance and the inductive reactance cancel out. So it's the frequency where 2 pi FL equals 1 over 2 pi FC. So, and we have to find, okay, what F does that occur at? What frequency does the capacitive reactance and the inductive reactance cancel each other out? So it's a little bit of just a kind of an ugly algebra problem. So if I multiply both sides by 2 pi FC, then I'll get 4 pi squared F squared LC equals 1. Everybody see that? I multiplied left side by 2 pi FC and right side by 2 pi FC and left side by 2 pi FC. So multiply these two together, I get this. Multiply 2 pi FC by 1 over 2 pi FC, I get a 1. So then I get F squared equals 1 over 4 pi squared LC. Take the square root of both sides and I get F equals 1 over 2 pi square root of L times C. So that's the frequency, also called F sub R. That's the resonant frequency. That's the frequency where the reactances cancel each other out and you're left with a purely resistive circuit at that frequency only. So at that resonant frequency only, you also have maximum current in this circuit because the ohms from here are canceling out the ohms from this component, and so you're only left with R, and the resistance is the number of ohms in this circuit is at its absolute lowest possible value at this resonant frequency. And so you get the maximum current at this point. At any other frequency, you have ohms added from XL and ohms added from XC, and the current will be even less in the circuit. So this is a condition of maximum current in this circuit. So if this is maximum current at resonance, voltage equals current times resistance. So V equals IR. R doesn't change, but current is at a maximum. So that means the voltage across the resistor is also at a maximum. I'm going to show you that on a plot here in a moment. Okay, so example problem. Determine XC at resonance. What is the impedance, meaning of the circuit? Below F, is the circuit more capacitive or inductive? Well, I'm going to guess that below F the circuit is going to be more capacitive because I said it was, and I showed you the plot that shows you that it is. So anyway, this problem, determine XC at resonance. So what at resonance? At resonance, XL equals XC, and it says XL is 500 ohms. So what is XC? XC must also be equal to 500 ohms. So trivial problem. What is the impedance? Z equals square root of R squared plus X total squared, but we know that X total equals absolute value of XC minus XL, and we are at resonance, so that equals 0. Z equals the square root of R squared, which equals R. So at resonance, Z equals R at F resonance. Below resonant frequency, we will find that XC ohms will exceed the XL ohms and the circuit will be capacitive. So, a little illustration. It says at the resonant frequency, the voltages across C and L are equal in magnitude. Doesn't mean that they are zero. It just means that they are equal in magnitude. So they can have a big voltage across them, but they will be canceling each other out. It's kind of shown right here. VC and VL are out of phase with each other, so they will cancel each other out, but they can have a pretty big voltage across it. And then down here in the bottom right is the voltage phasor diagram, which I've been drawing here all along as part of my explanations, but VL will be up, VC will be down, and VR is to the right. And then you subtract VL minus VC and you'll find what V total is across the L and the C. But at resonance, VL equals VC and they cancel each other out. So what is the resonant frequency? We can derive it like I already did, or we can just say, use the formula 1 over 2 pi square root of L times C. So 1 over 2 times pi times square root of, not reactances here, L times C. So it's 27 nanofarads. So that's times 10 to the minus 9th. And L is, the inductor is microfarads, so that's times 10 to the minus 6. So you do that calculation, and if you give me a moment, I will have that calculation. Okay, so I get 40.9 kilohertz. So this circuit is resonant at 40.9 kilohertz. At 40.9 kilohertz, what do we have? We have I is maximum. I can tell you what it is. I'll tell you what it will actually be equal to V source over R, because there is no reactance anymore. I is maximum. V across the resistor is also maximum at resonance. So I'm going to show you that graphically here. Here it is. So at resonance, I is a maximum, which is the value of it is V source over R. And anything on either side of the resonant frequency, the current will be less. The exact shape of this depends on the circuit, by the way, but all series RLC circuits will have this kind of behavior. So current will be at a maximum at the resonant frequency. Therefore, the resistor voltage will also be a maximum at the resonant frequency. The capacitor voltage will be a maximum as well at the resonant frequency, and so will the inductor voltage at the resonant frequency, but they will be opposite in sign. So one of these will be positive and one of these will be negative compared to each other. And this chart in your book doesn't really show it that way, but VC and VL will cancel each other out. And if you were to add up VC and VL point by point at different frequencies, you would actually get a plot that looks like something like this, the plot on the bottom right of this page. And you will see that the voltage across the inductor capacitor combination will go to 0 at the resonant frequency. So I think that's it's cool the way the circuit behaves. That's what you're going to do in lab today. So the next thing is I was going to show, because we're going to do more simulations in this semester, I'm going to show you how to do this on multisim, how to make a frequency plot. Here is actually a frequency plot, but it's not on this YouTube because this YouTube is now 45 minutes long, and I also need to switch computers because the computer I do this on doesn't have multisim, won't work on it. Multisim, my version, does not work on Windows 8. So that's all for first lecture. Welcome back to ETRO 122, and everything's good. See you soon. Bye.